let's look at another example. We're going to balance this redox reaction. Now again, sometimes they'll specify that this is done in acidic solution. This one I can kind of tell that it's in an acidic solution because they list hydrogen on the reactant side. They also list water on the product side, which those will come as a result of balancing this reaction. The first thing I like to do is split this into the two half reactions. And often you get kind of good at that. You know, like the hydrogen and the water, those are going to result from balancing this reaction. There's a lot of solutions, which means water is present. It's an acidic solution, which means hydrogen is present. So I'm going to guess that the two chromium particles probably go together, and maybe the two carbon compounds probably go together. To specifically figure out which one is oxidation and which one is reduction, then we'll assign the oxidation numbers. So let's see what we got. Hydrogen is just +1. In this dichromate ion, oxygen is always -2. There are 7, which gives me a -14. The particle needs to have a charge of -2 overall, so I need to have a +12 on the chromiums, making each chromium +6. In the ethanol molecule, let's go with the oxygen and the hydrogen first because they're always -2 on the oxygen, +1 on the hydrogens. So that gives me a charge of +6 on the hydrogen, -2 on the oxygen, for a total of +4. To make this neutral, then, I need the carbon to give me a -4, which means each carbon is -2. That feels naughty, but it's okay. Again, this is a covalent compound. We're not really transferring electrons. We're just trying to show how the electrons are being shared. Where are they closer? Chromium +3 is just +3. In carbon dioxide, this is a -2. Carbon's a +4. And +1, -2 in water. Okay, so we're looking for oxidation numbers that are changing. So it's not the oxygen, it's not the hydrogen. It's kind of what I guess, the chromium and the carbon. Oxidation involves losing electrons. When you lose electrons, your charge becomes more positive. That must be the carbon here. -2 to a +4. When I write the half reaction, I'm going to write the entire particle that contains the carbon. So this will be the ethanol, 5OH, turning into the carbon dioxide. Oxidation involves losing electrons, so I'll just write myself a little note. I think this is going to be the oxidation half. Reduction involves gaining. Reduction. If you gain electrons, you become more negative or less positive. That should be my chromium. And again, we'll put the entire particle. So it'll be the dichromate going to the chromium +3. Okay, so I got the two half reactions. And now honestly, when I balance these, I don't normally go through it as 9 steps. I split them, and then I think about the 9 steps in my head, but I kind of work them methodically. So the first thing I do is balance all the atoms besides hydrogen and oxygen. So let's do this carbon half. I need 2 carbons. Next comes oxygen. We'll balance oxygen by adding water. The product side has 4 oxygen, the reactant side has 1. We'll add 3 waters. Next, this is in acidic solution, although it doesn't state that, there will be hydrogen. I need to balance the hydrogen by adding hydrogen ions. My reactant side has 6 and 6 for 12. So we'll add 12 hydrogens to the product side. And then finally we balance the charge. I'm going to balance the charge by adding electrons. The reactant side is neutral, and since all I can do is add electrons, we'll add 12, that's a 1. We'll add 12 electrons and make the product side neutral as well. Now again, often something like this might fall into like a multiple choice question on the AP test, and maybe they'll say, you know, when the following redox reaction is balanced, what is the coefficient of blah, water or chromium or something like that? You cannot just balance this like a first year equation where you're just going side to side, balancing the chromiums, balancing the oxygens. You may get the atoms to balance, but you also need to have the charge balance. So if there's any indication that it's a redox reaction, you really need to go through this half reaction method. And it's fun. You're going to want to. Okay, that half is done. So we go to the chromium half. We balance everything besides the hydrogen or oxygen, which means the chromium. I need 2 of them. I'm going to just give myself a little more room. So we need 2 chromium. They were plus 3. Next, we balance the oxygen by adding water. So we'll add, 7 waters. Then we'll balance the hydrogen by adding hydrogen ions. Hydrogen ions. We need 14. Awesome. And then finally we'll balance the charge by adding electrons. On the reactant side, I have a plus 14 and a minus 2 for plus 12. The product side gives me a plus 6. And again, all I can do is add electrons, so let's go 6 of them on the reactant side. Now, one thing that I like about this point is that I originally listed the carbon half reaction as oxidation. Oxidation involves losing electrons, you betcha. I'm going to produce 12 electrons. Reduction involves gaining electrons. The chromium half reaction needs 6. Slight problem. The oxidation half is going to produce 12. All 12 of those electrons need to be transferred. So we're going to take this second half and we're going to multiply it by 2. Before we can add these together, I need to make sure that the electron transfer is the same. Awesome. So we're going to go through and multiply everything by 2. So hopefully this doesn't screw you up too much. I'm just going to write it right on here. This is going to become 12. Holy buckets. This is going to become 28. This will be 2. This will be 4. And 14. Awesome. Now we can add them up. First, we're looking to cancel like terms. We should always be able to cancel the electrons. Those 12 electrons are gone. And again, the other thing that I like to look for are hydrogen and water. It's real common that both halves may have hydrogen or water. For example, the oxidation half uses 3 water. The reduction produces 14. We can simplify that. Let's get rid of these 3, and we'll scale this down to 11. All right. Any other like terms? Hydrogen. The oxidation half produces 12. The reduction uses 28. So let's get rid of these 12, and we'll scale this down to 16. This is the real deal here. All right, let's add them up. Let's see what we got. In any order, what I have left on the reactant side is that ethanol. The water's gone, the electrons are gone. 16 hydrogen, and the 2 dichromate ions. On the product side, I have 2 carbon dioxide. Hydrogens are gone, electrons are gone. 4 chromium, and 11 waters. Yikes! Okay, let's see if all this was for hopefully the right answer. 2 carbons on both sides. A lot of hydrogen. There's 6 hydrogen plus 16 for a total of 22. Bingo, 22 hydrogen on the product side. Let's check oxygen. Reactant side has 1 and 14. There's 15 of them. Product side has 4 and 11. Yes, 15. And chromium, there's 4 on each side. Hey, this is looking good. We've got all our atoms balanced, so hopefully the charge balances. On the reactant side, I have a plus 16 from the hydrogen. And I have a minus 2 on the dichromate, but there are 2 of them. So that's a minus 4. So I've got a plus 16 minus 4 for a plus 12. What do you know? The product side, plus 12. So if you're feeling ambitious at the end, maybe you go through and add the phase symbols. These were aqueous. Carbon dioxide is a gas. Aqueous, and the water's a liquid. So that's where the hydrogen and the water will come into play in that original kind of skeleton equation that they listed. They'll come as a result of balancing this thing. Gosh, that's impressive. And kind of a lot of fun too.